We are very happy to have Netta from MIT, and she will tell us about the models of black hole evaporation. Please start.
All right. Thank you very much for the invitation. I wasn't able to come to my seminar, scheduled seminar, in the beginning of April. So it's nice to still be able to give a seminar. Though, of course, it's not quite the same thing, not being able to do it in person. I think I make an annual pilgrimage up to Berkeley. So this year it's going to have to be virtual. And of course, it's good to see all of your faces, even if it's remote. So my seminar today is on several different models of black hole evaporation, specifically in ADS, specifically for evaporating ADS black holes. And of course, this is all within the framework of the new hype about the information paradox in ADS CFT, the new developments. I remember when I was a graduate student, Joe Plotchinsky once described to me the progress on the information paradox as a long periods of boredom punctuated by short periods of frantic activity. And I'm pretty sure he was quoting Hemingway, who wasn't actually talking about physics, but regardless, we're in one of those very frantic periods of activity right now, so it's very exciting. And so these models of black hole evaporation are meant to help us along in this period of activity towards a better understanding of the information paradox, and of course, eventually how to resolve it. So the outline is pretty simple. I'm going to give a little bit of an introduction and some motivation. Not too much, because I think we're all pretty interested in quantum gravity, unitarity, and the information paradox. And then I'll talk about first a semiclassical model of ADS black hole evaporation. So this is based on the paper that I wrote with Ahmed, Don, and Henry in May, also related to the paper that Jeff wrote in May. The two came out at the same day. So there have been a lot of talks about this paper. And so instead of going into specific details, I'm just going to distill some of the salient points that I think are some of the major takeaways of what we got there, since many of you will probably have seen the perspective of at least one of my collaborators on this paper, since it's featured in a lot of different conferences at this point. And then after that, I'm going to talk about a somewhat classical, as opposed to semi-classical, model of ADS black hole evaporation. This is more recent work with Chris Akers and Daniel Harlow. And this will involve two different models of ADS black hole evaporation that are somewhat, they're definitely toy models and they're somewhat ad hoc, but they have some very interesting features that help clarify some questions that that are left over from the semi-classical model. So those are so there's three models, the one and semi-classical and two somewhat classical ones. And I'll wrap up with, I called it summary, but really it's a series of questions that I think are interesting and important right now, and mostly revolve around the gravitational path integral. So a few words about the information paradox. Now, I think most of us probably agree, at least most of us in this room, probably agree that quantum gravity is a unitary theory. But of course, resolving the information paradox is not, doesn't amount to all of us sitting down in a room, just having a powwow, coming out with the agreement that it's a unitary theory and then walking out. We need to actually have an understanding of the detailed dynamics by which the information gets out in the radiation. Just agreeing that it's unitary, of course, is not sufficient. Now, here I've drawn a picture of an evaporating asymptotically flat black hole. So here we have sigma prime, which is a time slice after the evaporation has completed, and sigma, which is a time slice before the evaporation is over, and two entangled pairs. So this is sort of a canonical picture. And traditionally, we use the volume and entropy of the radiation, that's minus trace rho rad log rho rad, as a diagnostic for whether we have information loss or information conservation. And normally we track this via what is known as the Page curve. We would compute the entropy of this thing as a function of time. This is in some sense considered a litmus test of unitarity. So here is the so-called two curves of the information of the, the entropy of the system. So we have the entropy of the black hole, which is this green dotted line here. And we have the entropy of the radiation, which is as computed by Hawking, which is the yellow dotted line here, dashed line, sorry. So let me just parse this briefly. So the entropy of the radiation, it starts out at 0. It starts out at 0 over here, and then eventually it increases, and Hawking's calculation would show that it just increases until eventually it reaches a thermal state and plateaus there. On the other hand, we have the entropy of the black hole, which we compute using the Bekenstein-Hawking entropy formula, A over 4gh bar. And this is just, so this decreases here. And of course, this at first seems a little funny because we all know about the Hawking area theorem. The area of a black hole increases as a function of time, but that assumes the null energy condition. So as soon as we allow ourselves to violate the null energy condition, and it is indeed violated by Hawking radiation, the area of the black hole can decrease as a function of time, and the Bekenstein-Hawking entropy decreases. Now, a unitary curve would look something like this. So this is the celebrated page curve. So here the entropy increases. So let's imagine we're talking about the entropy of the radiation for a moment. The entropy increases, but after the entropy is more than half the system, it had better start to decrease again, since the overall evolution would be unitary. So this then decreases as a function of time, and we end up at once the black hole is fully evaporated in a pure state. And of course, if we have a pure state before and after, and this is unitary evolution, then this would also be the page curve for the black hole. So this is in many senses, the litmus test of unitarity, whether we can calculate a page curve, an entropy curve that looks like this S unitary. So I should begin with perhaps a disclaimer. The page curve is not a panacea for solving all of our problems of the information paradox. A computation of the page curve by itself does not amount to a resolution of the information paradox. The entropy, after all, is a coarse-grained quantity. The resolution of the information paradox requires a fine-grained understanding of the state of the radiation and the dynamics of the system. Just calculating the page curve is not enough. It is not enough. However, a direct calculation of the page curve is nevertheless a significant step forward. And until recently, it was not considered as something that we could do in the broad community, given the tools that we had at hand. And in fact, if you asked me maybe 2 years ago, if this is something that we can do with the tools that we know, I would have said, no, you need to have some access to non-perturbative quantum gravity in order to calculate the page curve. So this was the general expectation, I think, in the community. You need to have access to extensive knowledge of non-perturbative physics. If you're going to calculate the page curve minus trace rho rad log rho rad, you're going to have to know essentially what rho rad is in fine-grained detail in quantum gravity. And so the biggest surprise for me in these new developments, starting in May and in many ways still unfolding, is that this is not true. You can calculate the page curve for unitary black hole evaporation just using semiclassical physics, and really, I should say, no direct input from non-perturbative quantum gravity physics. In other words, the tools that we're using are purely semiclassical. Now, I said no direct input for a reason. And the reason is that the calculation itself is semiclassical. All the tools we use are semiclassical. The calculations we do are semiclassical. But the interpretation of those calculations is heavily motivated by holography, or in the later papers, the replica wormhole papers, is motivated by the gravitational path integral. And in either way, either one of these is input from quantum gravity. It just turns out that we can get this indirect input from quantum gravity, which is enough, together with semiclassical physics, to actually calculate a unitary page curve. So today, I'm going to discuss both the original setup that was that Jeff did separately, and Ahmed, Don, and Henry and I constructed of the evaporating ADS black hole, where you calculate the entropy and find a page curve. So that's a semiclassical analysis. And I'll also calculate, as I said, this newer model of an evaporation process that is, I call it somewhat classical, in the sense that it exchanges the semiclassical analysis for purely classical analysis. But of course, you never get a free lunch. So you have to do this at the cost of dynamical topology change. And so this is the second model that I'll discuss, the somewhat classical model. Now, I should say that both of these models feature a so-called quantum extremal island. So this is this new formula that was proposed. And the rough idea behind this formula and the reason it was proposed is that in this original setup, what we did was calculate the entropy of the black hole. And essentially, if you want to say something about unitarity, you also want to show that the entropy of the radiation follows the exact same curve. And this quantum extremal island prescription essentially does exactly that. So both of these models, the original model has this quantum extremal island that was proposed by this AMMZ collaboration, and this somewhat classical model will feature some of the same ideas. So without further ado, let me begin with the semi-classical model of ADS black hole evaporation. Now, ADS black holes have an unfortunate tendency to not evaporate. If you want your ADS black hole to evaporate, well, you end up looking at a small ADS black hole. So small ADS black holes do evaporate, but of course we don't understand them very well. And by conservation of misery, if we take a black hole that we do understand, then it's not going to evaporate. So how can we model an evaporating ADS black hole? The qualitative setup is to do this by coupling it to an external reservoir that sits at a lower temperature. So this is the general idea. And in our paper, we did it using a two-sided case. So we start out with this two-sided black hole. And here you have a situation, so you have this bifurcation surface over here, which is the same for the right and left side. So you have a bifurcate horizon. This is the equilibrium situation. This is where we start prior to evaporation. And the method, as I said, is to couple it to a reservoir. So here we have the bulk, and we have a bath. Bath may not be the greatest term because it's cold, but maybe you just said an ice bath. So here you have a lower temperature system. And for some time, these are not coupled. But at some point, you couple the two systems, and essentially that gives you transparent boundary conditions. And so your black hole, which is at a higher temperature than the bath, is allowed to evaporate into the bath. And that way, we can force a black hole in ADS to evaporate. Essentially, what you're doing is you're just changing the boundary conditions so that the radiation doesn't reflect off of the boundary and get right back into the black hole, which doesn't give it a chance to evaporate. Now, it's actually rather difficult to do the calculations precisely, explicitly, sorry. Quantum extremal surfaces, which is what we're going to have to calculate, are hard to compute. And in ADS2, we can actually do this, you can do this explicitly. If you doubt that you can, that the two-dimensional results hold more generally, Jeff actually derived it more indirectly, but still very convincingly in higher dimensions as long as you have spherical symmetry. So again, I don't want to get too much bogged down in the details of the model, but I think a little bit of a review is probably appropriate. So just a lightning review. We work with JT gravity. So two-dimensional gravity plus a CFT. So I don't know if some of you are skeptical about JT gravity and whether it can be used to learn anything useful or interesting. I certainly was, and when Ahmed started at IIS, he told me he would convince me that JT was a useful theory for learning about higher dimensional gravity, and as you might guess, he certainly succeeded in that. As long as we extract universal properties of it, it certainly seems to teach us a lot about higher dimensional gravity. So here we have the action for JT. We have this topological term in the action. And then we have the dynamical gravity term. This is the boundary term over here. And also the CFT action. So this is JT gravity coupled to a CFT. And there's no explicit coupling between the CFT and the dilaton. Now, from the geometric perspective, this is a very boring theory. The metric is always ADS2. And so here is ADS2 in Poincare coordinates. Now, the fact that the metric is always ADS2 doesn't mean this theory doesn't have dynamics. The dynamics are just given by the boundary time u. And this the boundary particle, you can write this as a function of the Poincare time t. So you can rewrite this as a function of u, and you can get the Schwarzian action if you rewrite everything in terms of that. So there's a lightning review of JT coupled to a CFT. Now, we're going to take the bulk CFT to be in the Poincare vacuum. And to evaporate the black hole, we're going to do the following. So we consider, so here is the JT setup. We have U here is the boundary time. This dashed line is the event horizon. And we consider an auxiliary BCFT, which is in flat space with no gravity. And there's a time coordinate U over here. And this thing here is at 0 temperature. And what we do is we couple this at some time t is equals 0. We couple this to the same boundary time, the same physical time U in the bulk. And this results in a quantum quench. And there is which of course gives you a shock wave that propagates into the bulk, a positive energy shock wave. Now, the exact details of the shock wave depend rather in some detailed way on the way in which you couple these two. But you don't actually need to know the details of the shock in order to do any of the calculations that we do. The main thing you want to know is that you're able to put a lower bound on the energy of the shock by requiring the average null energy condition. So this just gives you a lower bound on what the energy of the shock has to be, and it's always going to be a positive energy. Any questions at this point? This is just an overview of how we do this. No questions so far. Okay, so now we want to do a calculation of the page curve. So we have an evaporating black hole. We forced our ADS black hole to evaporate. And we want to compute an entropy. We could do the thing which is the most obvious thing to do, which is just calculate the entropy of the CFT and plot it as a function of time. But if we did that, we'd be essentially just doing the Hawking calculation. We would be getting information loss. Indeed, we do get that if we do this calculation. And the reason is that we haven't put in any of the advantage that we get by working with ADS CFT. We haven't used the holographic dictionary. We went through all this trouble to force an ADS black hole to evaporate and then didn't use the fact that it's an ADS black hole, so it has a holographic description.
Can I ask a question?
Yes, please.
I guess my understanding was different from what you just said. I mean, while this was discovered in the context of ADS safety, where we had the RT prescription, in the end, the key advance was to ask directly what the entropy is and use the gravitational path integral to compute the entropy directly, as opposed to computing it from.
So that's right. So what I meant here is if you just do the calculation in the CFT not using the gravitational path integral. Just you do the naive CFT calculation.
Yeah, but in the end, we never needed the CFT for anything. I mean, it's just the gravitational path integral being used for the first time to sort of compute directly the entropy as opposed to.
Well, yes, that's right. I don't want to get into that because this is a Lorentzian calculation, and so far the replica wormholes, we've only really understood them. Well, I wouldn't say we've really understood them, but we've only seen them in the Euclidean context.
Well, I think that's the point. It is a Euclidean calculation. It's a particular Euclidean calculation, but it's in the same sort of, has the same flavor as, for example, Gibbons and Hawking being able to determine the entropy of a black hole from a Euclidean calculation.
Sure. I completely agree with that. My point is that the way, well, you could say a historical perspective, so far as at least we can think of Maya's history, is that the way that this was originally done is using holography, but in the end, the essential ingredient was the gravitational path integral. Yes,
right.
I agree with that.
The point is that the holography entered through a particular bulk prescription, the RT prescription, or its quantum generalization, and that turns out to just be a gravitational path integral. I mean, yeah. Well,
insofar as we know how to do the Lorentzian case with the gravitational path integral, which we don't explicitly yet. Everything is done by Euclidean path integral.
Sorry.
I would imagine that you would do a Schwinger-Keldysh type contour and everything works for the Lorentzian case, but it's also true that the Lorentzian path integrals somehow doesn't seem to be as smart as the Euclidean path integral, so we don't yet have a Lorentzian version of this replica wormhole calculation that I know of at least.
Well, correct me if I'm wrong, but I thought that the only input into the Euclidean path integral calculation that gives you the replica wormholes and gives you the right entropy is the state at one time, which of course you can imagine getting from some Lorentzian evolution.
Yes.
But it's ultimately that path integral just takes that state.
Well, yeah, but it needs a moment of time symmetry. So whether you have that or not, that was my understanding at least.
I mean,
I either way, I don't think it's essential. I think
Mark,
that,
I mean, the quantum extremal surface that appears, for example, in your setting is clearly not at a moment of time symmetry.
is what? Sorry, can you repeat that?
The quantum extremal surface that appears in your setting is not at a moment of time symmetry, right?
That's it's not in a moment of time symmetry.
Yeah, and that's the input for the calculation, though.
That is the input for this calculation. So I didn't see in either the West Coast or the East Coast paper a calculation which is exactly analogous to this. I mean, the West Coast model was a simple model where you had an end of the world brane, and it was a static case, and they just dialed up the number of flavors on the brane.
Sure.
And in the East Coast model, you had a black hole at complete equilibrium, eternally coupled.
Right.
So it's a little bit different from this setup.
Sure.
Yeah,
I think that
all
has
I'm
more to
saying.
do with how you maintain control over the calculation.
That's right. Yeah. So, I mean, sure, you could just jump through and say it's a gravitational path integral insofar as the quantum extremal surface prescription is justified by the gravitational path integral, rather than by assuming holography. Maybe this is what you're trying to say.
That's what I'm trying to say, yeah.
Okay, yeah. In that case, I agree with your statement. And my statement earlier about computing the entropy of the CFT and then giving you a non-unitary answer was explicitly a calculation that did not involve the Euclidean path integral. So just a naive calculation of the CFT entropy.
Right.
Yeah, that's right. Yeah, any other questions? Okay, so in other words, to summarize all this discussion, we need additional input if we want to calculate something which is unitary. And additional input comes in computing the entanglement entropy, in this case holographically. And as I will mention later on, you could do this using a gravitational path integral. So a brief reminder of entropy in ADS CFT. So let's begin with 0th order in GH bar. We have this prescription, which tells us that the von Neumann entropy of the reduced density matrix of the boundary in a region R is given by the area of a surface XR over 4GH bar, where XR is the minimal area surface that extremizes the area, or in JT gravity, the minimal dilaton surface that extremizes the dilaton. And if you want to go to one more order up in GH bar, you have to consider a contribution of the bulk entropy. So this is the bulk entropy inside of the entanglement wedge, which is the region in between XR and R. So I'll have a picture on the next slide. And as long as the boundary system is evolving unitarily, there's not going to be a time dependence of any of this. So so here's the picture. This green region in the interior here is meant to be the entanglement wedge. The surface out here is X sub R. And just as an aside, which is going to be important for this quantum extremal island business, the subregion duality states that the region, the bulk between, the bulk that is within this entanglement wedge, this green region, can be reconstructed from boundary data that lives purely on the domain of dependence of R. So what tells you that you need to modify the prescription in order to go to higher orders? So historically, here's how it worked. The consistency of the classical prescription, together with subregion duality, requires entanglement wedge nesting, which is the statement that if you shrink the region, the entanglement wedge also shrinks. Causal wedge inclusion, which is the statement that the causal wedge lives inside of the entanglement wedge. And strong subadditivity. So just something has to be satisfied. So strong subadditivity inequality has to be satisfied by entanglement entropy. And there are proofs of all of these in the classical regime, all of which rely on the null curvature condition. Now we run into an issue when we want to include quantum back reaction. So if we assume the bulk equations of motion, we have GAB is equal to the expectation value of TAB. And then we can have ordinary quantum field theory states that violate the null energy condition, in turn violating the null curvature condition, which means that in principle, entanglement wedge nesting, causal wedge inclusion, and strong subadditivity can all be violated by the HRT prescription once we include quantum back reaction. So this adding the von Neumann entropy term, just taking the area of the same extremal surface and adding the von Neumann entropy term doesn't help you because the surface itself can violate all of these. So this similar problem actually occurs in black hole thermodynamics. So the Hawking area theorem, which we want to think of as a second law of thermodynamics, relies on the null curvature condition. And as I said before, it's violated by quantum back reaction, violated by the Hawking radiation. So the area of the black hole shrinks as the black hole evaporates. So the resolution that Bekenstein proposed resolution that is now applied in general to quantum correct the area whenever the null energy condition is violated by quantum effects, We replace the area by the generalized entropy. Sorry, this sigma here should be a chi sub r, which is just the area of a 4GH bar plus the von Neumann entropy. So here's a picture. We have R, we have chi R, and the von Neumann entropy is evaluated on one side. And there's a large body of evidence that this generalized entropy is UV finite. In fact, there's a nice review of that in the quantum focusing conjecture paper. So that's where I usually direct people if they want to see evidence in favor of this. As far as I know, actually, there's no, this hasn't been determined for the graviton, although I would really love to know the answer if somebody has actually done this calculation for the graviton. Okay, so the quantum extremal surface prescription. So what Aaron and I did is we said, okay, let's take this quantity, this generalized entropy, and instead of computing it for the extremal surface, we're going to compute it for the surface that extremizes the generalized entropy. In other words, the proposal was that the von Neumann entropy of rho sub r is the generalized entropy of the surface that extremizes S gen, which we call the quantum extremal surface. And if you have multiple such surfaces, you take the minimal generalized entropy one. So again, it's the same picture from before. For a higher dimensional system, for the dilaton, we don't have this picture, but for a higher dimensional system, you have the boundary region R, and you have chi R, and you compute the von Neumann entropy of out, and you extremize the area of this plus the von Neumann entropy on this side over all possible surfaces. Now, if you use the generalized second law, so the generalized second law is the statement that the generalized entropy increases on causal horizons, and we often use it, we replace the, well, it's been used as a replacement of the focusing theorem until we had the quantum focusing conjecture. So using that, you can prove that this prescription satisfies causal wedge inclusion, even when the classical prescription might fail. As an aside, this formulation alone is actually not sufficient to prove strong subadditivity or entangled wedge nesting. For that, you need a quantum analog of Aaron's reformulation of HRT known as maximin. Now, there's a very interesting property of quantum extremal surfaces, which is very different from their classical counterparts, which is the failure of complementary recovery. So if you have a mixed state in the bulk, then it is possible for a quantum extremal surface of this region R to not be the same as the quantum extremal surface of the region R bar. In other words, the surface that extremizes, so chi R here, extremizes the generalized entropy computed with respect to this side, but it need not extremize the generalized entropy computed with respect to the complement. So you can have the situation where there is a gap between chi R and chi R bar. And this is the failure of complementary recovery. And at the time, Aaron and I thought that this gap would most likely always be Planck-sized. But one of the discoveries of the papers from May is that this is not necessarily the case. The gap can actually be quite large. So let's get back to the evaporating black hole. So before we evaporate the black hole, we have this picture here. This is a two-sided black hole, the left side, the right side. The quantum extremal surface here is this bifurcation surface, and it's identical for the left and the right. Now we couple the black hole to a cold bath, and we begin to evaporate it. Initially, the surface chi R moves continuously in a space-like direction towards R. But after some time, it jumps. So let me talk about this, this figure first. So for a while, so this is where the surface chi R begins, and then it moves in a space-like direction continuously for some time. This thing here is the shock. So it's positive energy shock. So we couple the system over here. The dotted line, the dotted blue line over here, corresponds to a new quantum extremal surface, which is nowhere near a classical extremal surface. And this solid blue line here is when that new quantum extremal surface begins to dominate, which is to say, when it has smaller generalized entropy than the other quantum extremal surface over here. And this gap between these two is quite large. This is not something, this is not tiny, it's quite big. And surprising in the sense that we have this quantum extremal surface, which is very far from any nearby classical extremal surface. So this figure over here is after this transition, which happens after the page time. So here we have this left quantum extremal surface. This is still quantum extremal with respect to the left side. We haven't done anything to the left boundary at all. And this one here is now quantum extremal with respect to the right side. And there is a gap between them due to non-complementary recovery, since the bulk state is now mixed. So this is what happens as a result of this transition over here. Now, if you were to take entanglement wedge reconstruction very seriously, you might consider the following statement. Well, we have the right boundary, the entanglement wedge is this region here. And the left boundary has this entanglement wedge. We also have the third system in the problem, which is the bath that absorbed all the Hawking radiation. And we have a third system in the bulk, which is the region in between these two. Perhaps very suggestive is the fact that if you take the bath that was this auxiliary system and you dump it into the left system, then you'd expect that the entanglement wedge of the left side now includes all of this region over here. So in particular, this moves to include this in-between region. And the hypothesis in these papers here is that the gap between chi-L and chi-R is just the entanglement wedge of the radiation. That this gap over here can be reconstructed from the radiation. And the existence of this gap, of course, appears to be synonymous with the failure of complementary recovery due to the fact that you're extremizing over a mixed state. And this is what gave rise also to this quantum extremal island prescription. So the proposal that the region between chi-L and chi-R is the entanglement wedge of the radiation, this is what led AMMZ to propose this quantum extremal island formula, which computes the entropy of the radiation using the quantum extremal surface for this right side. And it's necessary. So I should have said in the last slide, which I didn't, is that this jump in the quantum extremal surface is necessary for the turnover in the page curve. So it's necessary for maintaining unitarity. And if we want to view this, so that's the page curve that's computed for the black hole. And if we want to view this as also the page curve for the radiation, then this quantum extremal island formula is really what's necessary. This is what essentially tells us that the page curve for the radiation and the page curve for the black hole are the same, and that we have a unitary evolution for our system. So I make a few comments here about this semi-classical model. So we do, yeah.
So I want to just make one comment, which, though I think that wasn't maybe appreciated in these original papers, I think that the complementarity property is not as speculative as as was maybe originally thought. I mean, I think it follows directly from the usual RT or quantum RT Engelhardt wall generalization, when you, instead of extracting the radiation into a separate system that's completely outside of the original spacetime, you simply extract it into a localized reservoir. This is something that Maria and I pointed out.
Yeah, I agree with that statement. Yeah, it's a very natural generalization of the quantum extremal surface prescription. I agree.
Well, again, I would argue that it's not a generalization at all. It's a direct consequence of it in the right setting. You'd have to sort of bend over backwards to say that it should be different as soon as you extract the radiation to an auxiliary system.
Well,
but these islands already appear in the case we studied.
To play devil's advocate, you might have said, well, how do you know that the radiation is really has any holographic description whatsoever? There is a sense in which you could have argued that.
Right, which is why it's cleaner to make the argument in a setting where you just localize the radiation in the original bulk in some reservoir.
Oh, this is you mean in the paper that you and Maria wrote, for example?
Yeah.
Yeah, sure.
But then once it's established in that context, it would be bizarre if you suddenly change the answer once you take the radiation outside of the original space.
Localize it somehow differently. I agree with you. Yeah. So to briefly summarize, so we do a series of semi-classical operations. These have no non-perturbative physics beyond the interpretation of quantum extremal surfaces as computing an entropy. And these allow us to calculate a unitary page curve, which is pretty remarkable. But of course, as I said before, the page curve is not the end all. We still don't have a complete understanding of what's going on. And one thing which has bothered me a little bit initially is that in principle, without any input about our system could be the low energy effective theory of some unitary and also a non-unitary UV completion. You could imagine, especially in JT, that our system is is a low energy description of both a quantum theory of gravity with unitary evolution and some pathological quantum theory of gravity with non-unitary evolution. And the quantum extremal surface prescription correctly computes entropy only in the unitary theory, which suggests the following possible concern. What if the quantum extremal surface prescription just spits out a unitary answer regardless of whether the UV completion is unitary or not? And if it's just an automaton that always tells you it's unitary even when it isn't, then it's not a very good prescription. It's not the page curve calculated in this way is not a very good litmus test. So the question is, if we had a holographic non-unitary theory, would quantum extremal surfaces give us a non-unitary answer? They had better if they're any good. Now, this is very difficult to see in this semi-classical JT model.
Netta?
So, yeah.
This seems, I mean, do you think that such a theory exists?
Well, certainly you could consider, in JT itself, if you just do the naive UV completion, is not a very good quantum theory of gravity. So you could worry about something like that. I don't think that in general.
Well, in JT, we know that it's dual to an ensemble of theories.
Yes, that's right.
So if you evolve a state with that ensemble, of course, it'll look like it's not unitary. But to the extent that you think such a prescription makes sense, I mean, to a physical observer that would actually, form a black hole and let it evaporate, it sounds like you're opening the possibility that there are consistent theories that in which it could go either way, information is lost or not.
So I don't subscribe to information loss. Let me put that out there. I don't subscribe to it. I don't think that's the correct description. However, and yeah, I don't think that quantum gravity loses information. But if I'm going to, I would like to either know why quantum extremal surfaces give us the right answer, or at least I'd like a model where the unitary answer is not the right answer and they don't give us unitarity. Otherwise, there's no test where we know that the fact that it gives us a unitary answer is at all meaningful. So in the absence of having a non-perturbative quantum theory of gravity where I can just immediately say, here's what the page curve, here's what the gravitational path interval exactly is doing inside this little black box, I'm going to give you a model which is in principle holographic of information loss, which I don't subscribe to, in which quantum extremal surfaces really do give you the right answer, which is in that case, non-unitary evolution.
Would you have said about ADS-CFT that it's meaningless because the CFT just always tells you that the evolution is unitary?
Well, that depends on this. Yes, in a particular example of ADS-CFT, I agree with that. Why don't I get to the model, and then you can we can fight it out at that point. Does that sound good?
I'm not the fighting type. I'm going to go back in my shell now.
So it's hard to see in this model. A simpler model would be nice, but what could possibly be simpler than a semi-classical picture? Well, obviously a classical picture. So we already have there's one classical picture of the black hole evaporation, this 3D holography within holography picture, and we're going to have a different version, a different model, which is just going to be highlighting other features, and it's simpler in many ways. So moving on to a somewhat classical model of ADS black hole evaporation. This is work with Chris Akers and Daniel Harlow. So I guess, yeah, Chris was an alumnus of this group. So we're going to work with a toy model. This is very much a toy model, beginning with a unitary, it's going to be unitary evaporation. So the black hole is going to evaporate via the emission of smaller black holes. So these are going to be our stand-ins for the Hawking quanta. Now, the emission of a black hole is going to result in a wormhole with a new exit. So we have a large black hole and it's emitting Hawking quanta, which are being modeled by small black holes. And each one of these is a connected wormhole with a new exit. I'll have a picture on the next slide. The important thing is that at least in ADS-3, we can get time symmetric geometries like this just by cutting Riemann surfaces. We can just take different quotients of ADS-3. So we know how to do this in ADS in 3 dimensions. So here is the model. So we start out with, so here's our black hole CFT, and we're going to take our Hawking quanta, our emitted black holes to be holographic. So we have, so each one of these corresponds to emitted Hawking quanta. And so this here is these are the Hawking radiation CFTs. So at each time step, we have a topology change. So this is very much of a toy model. And we gain another exit. So each time step, there's going to be a change in here. So the pair of pants acquires a new leg, and I guess you have to revisit the tailor every time. So then you have another step here, and you gain another leg. This is inspired by the idea that entanglement builds geometry, and this is sort of a classical version of the quantum octopus in ER equals EPR. And we're just having these connected wormholes as stand-ins for the entanglement. And again, this is a very much a toy model. We would imagine that we want to take the quantum limit of this, where the wormholes are very, very small, to get anything remotely resembling a realistic evolution. So, just any questions so far? I haven't finished explaining what the model does yet. Just so I suppose that we've been using technical terminology here. I think it was invented by Daniel. So there are two minimal surfaces. So each of these is a time symmetric slice. And there are two minimal surfaces, and the technical terminology is that this is known as the sweatband, and these are known as the ankle bracelets. So we have two possible candidates for the RT surface. Let's say the RT surface of the Hawking radiation. Now, this is a purely classical model. We don't have to worry about the entanglement of the bulk quantum fields, which means that the calculations are quite simple. Each one of these gammas has the same area. And when we are very early stages of the radiation, of the evaporation process, what happens is that we have very few of these gammas. So the area of these gammas is much smaller than the area of gamma prime. So the RT surface for the Hawking radiation is going to be the union of these gammas, and the entanglement wedge of the radiation will be very small. As we evolve with time, eventually we're going to reach a point, I think this is explained on my next slide, yeah. Eventually we're going to reach a time at which we have so many of these that they outweigh the area of the gamma prime, and we get a jump. So the area of gamma prime now becomes the gamma prime becomes the new RT surface because it has smaller area. So the gamma prime becomes minimal, and all of a sudden, the entanglement wedge of the radiation is now the entirety, almost the entirety of the bulk. So there's a jump from when it was very, very little to when it became essentially almost all of the bulk. So I'll say a few more words about this model in a moment, but what's nice about this is that it results in a page curve. So we get an increase in this until we get a turnover when we have the phase transition from the disconnected many exits to the connected bifurcation surface of the original black hole. And then it keeps on decreasing with time. So this very simple, maybe silly toy model does have a page curve. Now, there's also an island in this model. So it's just the region that's between gamma and gamma prime. So the Hawking radiation is a series of holographic CFTs. It's a difference from the original setup, but we go from having just very little in its entanglement wedge to having the entirety of the black hole interior inside the entanglement wedge of the radiation, which is effectively the prescription of the quantum extremal island. So in particular, what's nice about this is that the island phenomenon in this example, in this model, appears to just be quantum error correction. So one way to see this in a very simple way is just if you consider your, say, at late times, but you pick too few of the radiation CFTs, then you're not going to see the island in their entanglement wedge. If you maybe add the black hole or you add enough of the radiation CFTs, then you do get the island. So this appears completely analogous to the picture that is often drawn of the three intervals in ADS, where if you have just one of them, you don't get the point in the center, but as soon as you have two, you do get the point in the center. So this has very similar features, appears to be standard quantum error correction, the way that we recover the island. And so this very simple model still highlights a nice and interesting feature of the island. Now, let's ask a potentially controversial question, which is what would a holographic calculation of information loss, so the Hawking calculation, what would it look like? Again, I want to preface this with a disclaimer. I don't subscribe to information loss. I'm pretty sure my co-authors don't subscribe to information loss. This model is a thought experiment for understanding what would be different if we did a holographic calculation of information loss. So here is a toy model for information loss. So here we have a black hole, and again it emits these smaller black holes, but this time there's no ERB between the black hole and the Hawking radiation. Instead, the Hawking radiation is connected to another CFT, which is our stand-in for the baby universe. And with time, we get more and more of these, which are each entangled with their own quote unquote baby universe. It's not really a baby universe because it's got a boundary, but this is what our stand-in is for this in this model. So what happens over here with the extremal surfaces? So here we have gamma prime. So gamma prime is a minimal surface for the black hole. And gamma is the minimal surface for each one of these of the Hawking radiation together with the baby universe. So what happens to the information here? Well, okay, let's compute the entropy of the Hawking radiation. Well, at first it's just gamma, and at the second time slice it's 2 gamma, or 2 of the area of gamma. And as we evolve forwards with time, we get more and more and more, and it grows. It doesn't have a turnover where it starts to decrease again. Now, gamma prime here is totally irrelevant to the problem at hand. It's never going to be homologous to the Hawking radiation, so we don't care about it. So what happens is we can use the extremal surface prescription successfully to get information loss if it were the case that our holographic theory actually had information loss. So it means that the HRT, HRRT, FLM, AW proposal doesn't just give us a unitary answer. It gives us a unitary answer because the underlying theory is unitary. Of course, again, we don't think information is lost in a realistic quantum theory of gravity, but it's nonetheless useful to have this thought exercise to see what the quantum extremal surfaces would do if they were actually calculating information loss.
Netta, can I ask you about this?
Yeah.
So in the second model, I mean, this is very schematic, the pictures, but I think if I wanted to compare that to something like ADS-CFT, what's happening, right, is that at every step you're creating another asymptotic boundary.
That's right, yeah.
Is that right?
That's exactly right, yeah.
And I'm just sort of struggling with what sort of theory would do that. I mean, it's one thing to say I can transfer information from my boundary into an auxiliary system, but in that case, this doesn't happen, and we would actually keep track of the information.
Well, you could ask the same question about the previous model, in which case what I would have told you is, you could think that the universes, the asymptotic boundary always existed, but you sort of created this wormhole between them.
Well, in the previous model, I could have asked the same question, but you weren't using it to come to a conclusion that I'm troubled by. So, but I agree that I could have asked the same question.
That's right.
I guess my question is, I think what I'm trying to say is that if you need to create additional asymptotic boundaries in order to lose information in gravity, then I think you've just proven that information isn't lost.
I agree with you. And this model is certainly not meant to advocate information loss. And perhaps I haven't been clear about that. This model is just meant to say, suppose we really wanted to model information loss just to see what holographically it would look like. I think, yes, I think we are forced to the conclusion, at least in this particular case, that we have to nucleate new asymptotic boundaries. That seems incredibly unreasonable. I don't think that quantum gravity would do that.
Netta?
Yeah.
Is it possible that if any baby universe has only one-dimensional Hilbert space, as somebody saying, and so this can never happen? Is it true? Maybe Hawking radiation increase,
yeah. So again,
entropy, and then you don't have anything to entangle, so you can't do this.
So let me be clear. This model is not meant to be the only way to model information loss, or the proof that information loss doesn't occur. It's meant to show how quantum extremal surfaces might behave in a way that would give you information loss. Basically,
yes,
to ensure that there is no, that the quantum extremal surfaces, that the answer quantum extremal surfaces give you actually depends on the dynamics of the theory and is not a kinematic object which doesn't have much meaning.
I agree. Your unitary is usually a choice, right? Even in an anomaly for global symmetry in the usual case, instead of choosing global symmetry to be non-anomalous, you choose gauge symmetry to be non-anomalous because you want to keep unitarity, right? Certainly, in path integral, you include the wormhole or not is your choice, and that's true. But I was going more that if baby universe, isolated baby universe without any connection to the outside is usually like if the dimension of the Hilbert space is always 1 for as some people say, and then that dynamics may kill this. Is it true? Or
the dynamics, sorry, can you just repeat that?
Yeah, because Hawking radiation is a particle. You can have a two-dimensional Hilbert space, but baby universe can't. And then you can't have entanglement entropy or abandonment entropy increasing.
I agree. Yeah, this picture was not appropriate in that situation. Yeah. I would agree with that. That's right.
So that may even be yes. Okay. So that may select the model.
I mean, I put baby universe in quotation marks here because this thing has a boundary, so it's not really a baby.
Yeah. But I think you're imagining that without boundary, but it's decoupled from everything, right? So that's.
I mean, this is just a way of so we need it to be holographic so we can use the quantum extremal surface, or in this case, the classical extremal surface prescription.
Yeah, so you're saying, okay, all right.
This is a very ad hoc toy model, just a way of showing that the prescription really does work regardless, to give you the right answer, regardless of what the right answer is. It's going to give that to you.
Yeah, that part I don't have any issue.
Yeah. So one question that this raises, so this is how we would model information loss in this silly toy model that's purely classical. And in some sense, we could say this is what the Hawking calculation might look like. But in a more realistic model, where the semiclassical evaporation process, where we actually have unitary evolution, is there a way to describe the Hawking state, the Hawking calculation, using quantum extremal surfaces? So the wrong quantum extremal surface maybe is that the way that we can model the Hawking answer of black hole evaporation in a model where it actually evaporates unitarily. In other words, how do we compute what Hawking did holographically? Now there's a final comparison here that is kind of fun that I want to do, and just to really drive the point home that I don't support information loss, you'll notice that only the unitary process is smiling. So let's take a look at these two pictures. Now, in the top picture, we might have said that the wrong Hawking calculation corresponds to always using gamma to compute the entropy of the radiation, even past the point where over here, gamma is no longer dominant. So you might have said that's the Hawking calculation, the holographic version of Hawking's calculation. We forget about the minimality requirement and we just always use gamma. Now, in the bottom picture, we would have said the wrong calculation is to switch between gamma and gamma prime when gamma prime has smaller area than gamma, even though gamma prime is not homologous to the Hawking radiation. Now, that answer would have actually given us information conservation if we had used the wrong extremal surface, if we'd used gamma prime, even when we had to keep using gamma. So the takeaway is that using the wrong saddle, forgetting about minimality or forgetting about homology, gives the wrong answer. But the wrong answer for a given theory, for say this sick theory here, can actually be information conservation. And I find this to be very good news because it tells us that the quantum extremal surfaces that we found compute the answer for a unitary theory, and it's non-trivial that they do that. So I think I'm pretty much at an hour. So let me make a few broader comments here. So some comments about the replica wormhole papers. So in the replica wormhole papers, there's a Euclidean gravitational path integral calculation that justifies the island formula. So we can calculate a page curve using semiclassical physics as long as we're also willing to use the gravitational path integral and saddle point approximation. So we don't necessarily have to just go with holography, we can just use the gravitational path integral. But to ultimately address this issue, what we need to have is a better handle on the gravitational path integral itself. So this thing is a little bit like a black box. It calculates things correctly rather miraculously, and I think we don't really know why. I for one would like to know what entropy is it actually calculating? In other words, how does it know what entropy to calculate? And in particular, how can we compute the same entropy without using the path integral? If I wanted to do a minus trace rho log rho calculation, what is the rho that I need to put in to get the answer that the Euclidean path integral is getting out?
Why isn't the answer just the state of the conformal field theory?
Yeah, it is the state of the conformal field theory, but I'd like to understand this on a gravitational level.
Are you sure that you can?
No, I'm not sure that I can. If I can't, I'd like to know why.
I think the bigger miracle, I think by far the bigger miracle is that you can at all understand anything from the gravitational path integral.
You know, I would buy that, except for the fact that 2 years ago we would say that about the page curves. So
no, sorry, that's not what I was saying. I was saying the opposite. I was saying it's a miracle that we can get anything from the page curve was a miracle. It's perfectly consistent.
I guess, what can I say? I'm young. And I hope that I have many miracles ahead of me.
Oh yeah, no, there may be a lot more. I'm just saying it's
right.
Anybody's guess, right?
Yeah. It's possible that we can't. And if we can't, then I think that ultimately, I think the crux of this is understanding the gravitational path integral better, whether it's what is it calculating and how it's doing that, and whether it's, well, there's just the connection with an ensemble, whether it's calculating an ensemble or not, what self-averaging, how does that go into this? So relatedly, I guess I put this here, the quantum extremal surface prescription can give us an answer which is both information loss and information conservation, depending on the dynamics of the theory and the fine-grained structure of the state. So this is basically the same as the last bullet point, which is what is the fine-grained state whose entropy is computed by the path integral? And as Raphael said, it's possible that we can't get this answer, but I think we still have to try for it. And in the same vein, what does an observer outside the black hole actually measure? And is the path integral actually computing an ensemble average? How do we figure this out? What kind of ensemble average? What happens for n equals 4 super Yang-Mills? So the crux of all of this, in my opinion, is unlocking the black box that is the gravitational path integral, understanding better why it knows what it knows and how much more we can get out of it. So with that philosophical note, I thank you very much for your attention.
Any further question for Netta?
Maybe just kind of straightforward one. Yeah, I think this good. Like you're saying, the problem of the Hawking calculation is that it didn't allow the choice between unitarity and non-unitarity. But in this way, of course, you can at least choose to define the theory, whether you want to define unitary theory or not. And so, like in the gravitational path integral, to include a wormhole contribution or not, or in your dynamical, into your toy model, which one you take. And I should have known, but is that in the QCD case, is it theoretically solved that you usually need to include instanton in your calculation because of Eta prime problem and so on, right? Because we have an experiment. So you have to solve this U1 prime problem that goes from boson. You have to have anomaly and the Eta prime must be massive, so you have to include. And then if you include that, then you have a strong CP problem, so usual story. But instead, if you just limit a path integral to be just n equals 0, non-winding sector of the instanton.
Sorry, the path integral, can you just repeat that last bit?
No instanton number equals 0 sector. You just limit that.
Okay.
As a definition of QCD. Yeah. Then you certainly don't have a strong CP problem and so on, but still, then it doesn't match with the experiment.
Okay.
But that's a choice, right? If you include some non-perturbative saddle point contribution of the path integral or not. So that reminds me, like Euclidean wormhole must be included or not included. If that's the choice, in QCD case, do we know that we have to do it, or just we usually, we don't know, both may be consistent non-perturbative definition, but experiment choose one over the other? I just forgot, or maybe not known, I don't know.
So I think right now, especially if you look at something like the East Coast paper, they included because they can.
Yeah, okay.
And they, in fact, there are comments, well-placed comments in the West Coast paper that are not in the East Coast paper about the fact that if you do include these connected saddles, then of course you run into the issue where you don't have factorization the way you'd expect. So, there's something else that, I mean, if you're working specifically in a situation where you're doing some averaging over coupling, then that's okay. But if you're working with n=4, then there's a question of what comes in to save the day as far as factorization.
Oh yeah, just choosing the holographic theory to be n=4 or something, you're already choosing the theory, you know, in a unitary way.
Sorry, can you just repeat that one more time?
If you're already saying the holographic theory, or maybe only well-defined theory is n=4 super Yang-Mills, then you're already choosing, you're making that choice, right? So
making which choice?
Oh, the choice is whether you're unitary theory or non-unitary theory, whether you include.
Oh, I agree with you. I just don't think that we know with a theory like n=4. I don't think we know if we get to include the replica wormholes or not. I think we might be able to include them, but if we do, there has to be some other effect that comes in to resolve the issue that you know we don't have factorization the way that we would expect in an exact theory.
Yeah, my just question was, I mean, if QCD already has the same kind of issue or not, but.
I see.
Yeah.
I have a pretty simple question.
Yeah, actually, can I make a comment? I forgot to unmute my microphone.
Yeah, go ahead.
Yeah, so just about the QCD thing, I think the answer is that there is a principle like cluster decomposition that forces you to take particularly in a combination of those n vacua rather than the theta vacuum.
Okay,
I don't think that there is anything. I don't think there is a similar thing that I know of in quantum gravity, but in quantum field theory, there's the cluster decomposition that kind of forces you to take a particular vacuum and not other.
So you need to have probably something like similar kind of principles. Of course, you could take unitarity as that, but yeah. Okay, great, thanks.
There might be something, but I don't know which one it is.
Mm-hmm.
Yeah.
Yeah, so I was wondering if you have any thoughts on like what techniques or what avenues will actually be interesting to understand the gravitational path integral better?
Well, I guess as it happens, I'm working on in this direction. So I think we need to understand a little bit better. Let me put it this way. There's another system that has a very similar structure, which is the spin glass. So spin glasses have the same sort of replica wormholes so these occur after a phase transition from the paramagnetic phase to the spin glass phase. And the calculations for the spin glass are quite explicit. And there is a very interesting averaging that they do in a very particular way that I think can teach us a lot about the averaging which is implicitly done for us in the gravitational path integral. So I'm hesitant to say more because it's I guess not entirely clear how far the parallels go just yet. I should say this is work with Sebastian Fischetti and Alex Maloney. But that at least appears to be one direction in which is giving us potentially promising information about what happens. So that's sort of looking for other systems where this type of phenomenon occurs and understanding it there. That seems to be promising.
Yeah, I guess it's surprising that spin glass, like a simple like Ising type model, I'm guessing is.
Yeah, if you take a look at the random bond Ising model with all-to-all coupling, it's a very simple model where you have this exact type of transition from disconnected to connected replicas. They don't talk about it like that, but right. If you look at the formulas, that's exactly what's going on.
I see. Cool, thanks.
Yeah, I mean, for them, they do an average over coupling. So they do a disorder average. And that's what, well, understanding how they do that disorder average can be potentially very informative for understanding the gravitational path integral, since there's a lot of similarities between the two.
Hi, can I ask a very naive question?
Sorry, what was that?
Can I ask a very naive question?
Of course.
For the Euclidean gravitational path integral, suppose you can do Euclidean when you analytically continue to the Lorentz signature. Is always you can do it anisotropy for a graviton?
If what? Can you repeat the question more slowly? My internet is a little choppy.
Okay, I'm trying to understand. Suppose you can calculate Euclidean gravitational path integral, then you analytically continue to the Lorentz signature. You can always do it, or there's an anisotropy?
So I suppose if you look at the gravitational path integral and the Euclidean slice, then yeah, I mean you can do an analytic continuation. Everything is from the t equals 0 slice. The problem is usually more if we have Lorentzian spacetime, which has non-trivial time dependence, then you can't find a moment of time symmetry in which to do an analytic continuation to the Euclidean path integral.
Okay.
So there isn't a one-to-one map between the Euclidean path integrals and spacetimes you can prepare from with Lorentzian, which have Lorentzian evolution.
Okay, because I asked some question because people are thinking this will Wilsonian effective theory. They always using this Euclidean signature. You talk about this why hard momentum cutoff, then you analytically continue to the Lorentz signature. And people saying that in the gravity case, there will be very large subtlety when you're doing this analytical continuation. And the Wilsonian picture may be wrong. So I'm not sure if...
So I'm not sure I 100% understand the question.
No, this is not a question, just,
okay.
just a little comment. No, it's okay. Thank you.
So Netta, do you have any comments on what you think the islands formula and the replica wormholes tell us about firewalls?
Way to ask a trick question. You know, I don't think we've solved, we certainly haven't solved the firewall problem. And I don't, well, of course, it's interesting what we see in terms of entanglement wedge reconstruction with this island formula. I don't see how entanglement-based arguments are going to get us out of Merrill-Polchinski. I don't see how that's something that understanding the replica wormholes is going to help us with. So I think maybe we can explain away the various entanglement-based arguments for firewalls, but Merrill-Polchinski doesn't really use entanglement. And so I don't see, I guess I haven't seen anything that's convinced me that we're on the right track for resolving that directly.
I see. But do you think like the existence of these islands maybe tells us a little bit about the like fine-grained state, in the sense that maybe there's like some non-factorization that's happening between the black hole degrees of freedom and the radiation degrees of freedom, which, you know, could help with firewall, like, you know, potentially help with firewalls, at least for like atypical states. I agree that the Merrill-Polchinski thing is not going to be answered by any of this. Yeah,
I suppose I don't view anything we do with atypical states to be that useful, because at the end of the day, firewalls are, the strongest part of firewalls is about typicality. So in that sense, it's not clear to me how much we're going to learn. Nonetheless, understanding any aspect of the information paradox, of course, we have the hope of understanding more of it as a consequence. So potentially, yes, understanding something about the factorization of the Hilbert space could help, but the typicality is an issue. It's a problem, and I wouldn't buy the firewall arguments. I wouldn't think that, I don't think that atypical black holes necessarily have firewalls. So I don't see immediately how that's going to help us.
Oh, are you by Merrill-Polchinski, are you kind of referring to this typicality thing? Yeah.
Typicality, I mean, their conclusion about state dependence, they need a very large amount of state dependence, and that's not something that approximate quantum error correction.
I know. Yeah. then just the one solution, or not solution, or direction could be like what the semiclassical vacuum and what the excited states. That's what I've been doing. Just this is propaganda, so forget about it. But what is a vacuum? And black hole is typical, but you have to say what the black hole vacuum, what that corresponds to in a microscopic level, and an excited state and what. So that might we're calling hard mode and soft mode and stuff. But yeah, yeah.
Any further question for Netta?
Actually, I had one more kind of dumb question. So, so you were talking about how you want to see how the Hawking calculation would come out of the quantum extremal surface prescription.
Yes, and I guess I should say that's work with Chris and Daniel in progress. Sorry, I should always list my collaborators. Yeah.
So I kind of a dumb question, which is there some sense in which the quantum extremal surface prescription is theory dependent, in the sense that, for example, I can quantize JT gravity without including other topologies, just the disk topology, and then in that case, if you do the entanglement entropy calculation, you would just get Hawking's like curve. You wouldn't get the page curve.
That's right.
If you included this the other topologies, then you would get the page curve. Mm-hmm. If you apply the if you derive the quantum extremal surface prescription starting from the Euclidean path integral, knowing that your theory doesn't include other topologies, then presumably you would land on a quantum extremal surface prescription that never had islands in it.
That's right.
Right. Whereas if you included the other topologies, then you would get islands.
That's
so
right.
Is there some sense in which I should think of the quantum extremal surface prescription as depending on the way I like quantize my theory? It's not like just one statement that's just true no matter what theory I have.
Yeah, absolutely. I mean, this was kind of the point of models 1 and 2, the unitary and the non-unitary, which is that the quantum extremal surface method really depends on what it gives you, and which one you choose really depends on the theory. So for example, if all you had access to was in that case was you just knew what the black hole was and you knew what the bifurcation surface was, you wouldn't necessarily know what the topology behind it is and whether you need to use the two different prescriptions, the one that gives you the wormholes or the one that gives you the baby universes. And so which one you use is just really theory dependent. So the prescription that you would use, the quantum extremal surface that you would that would be calculating the entropy, is definitely theory dependent, and I think it's a strength, not a weakness.
Okay, thanks.
But that doesn't resolve the question of how do we recreate Hawking's calculation in the unitary theory, because Hawking calculated what he calculated in a theory that ultimately we believe is unitary. So the question is, what did he actually calculate? Is there a holographic derivation of that?
I'm not trying to understand the question. I mean,
he presumably calculated a coarse grain entropy, and I just want to know what that entropy is in terms of the boundary quantities.
Is it obvious? Is that obvious that his calculation maps onto some entropic calculation in the unitary theory?
So in model 1, it certainly does. It's just you just use the wrong extremal surface, and then you can do a prescription the way that Aaron and I did, which gives you the it's the entropy of some. It's a coarse grain entropy. It's a very particular type of coarse grain entropy, and it would be nice to understand exactly how this works in the semiclassical case.
I have a proposal.
Raphael looks very perturbed. Yeah.
Yes. No, I'm not perturbed. I'm perturbing. I have a proposal that I mean, I'm not sure I fully understand the question, because reproducing Hawking's calculation in a unitary theory seems to be a contradiction in terms. I would want to, I mean, Hawking's calculation got you a non-unitary answer, so you better reproduce it with something that's not unitary.
It's just a coarse grain entropy.
But I think you've already discovered a way of doing it, right? If you use JT gravity, that's dual to an ensemble of theories, and you just run Lorentzian evolution with the entire ensemble, and it maps a pure in state to a mixed out state, and this works, right? So now you've got a
it's a little bit indirect, but yes, that is the idea.
I mean, how is that indirect? Right? It isn't the, well, I guess I would argue the only way to understand how you can have a calculation in the bulk that tells you on the one hand that the out state is mixed, and on the other hand that the entropy is 0, is if it is an ensemble average.
I agree with you on that. I don't, but I think it's really two different calculations. I'm viewing one as a calculation of a fine-grained entropy and another as a calculation of a coarse-grained entropy.
I don't see the contradiction between what we just said. I mean, if the ensemble average of the entropy would be 0 and the average state would have non-zero entropy.
Yes, I agree. But I think if I understand correctly, you're talking about the entropy that's computed by the dominant quantum extremal surface. Am I right?
Yeah, I'm talking about the entropy that's computed from the RT prescription.
Right. I would say that's not the Hawking entropy, since it's.
Well, I don't know. It's the average entropy in the ensemble, which is 0 because every single member of the ensemble is unitary.
Yeah, I agree with that.
Yeah, but the state computed in the same gravity calculation is going to be mixed, which is consistent with it being the average out state produced by these.
I agree with that statement too. What I would like to know is, and maybe this is not 100% in keeping with the interpretation of an ensemble average, so but potentially there's an issue there. But what would be interesting to know is what is the state? So Hawking calculated the entropy negative trace rho log rho for state rho, and I guess I would like to know is what is that state rho holographically and in terms of the CFT, and maybe that's not consistent to ask if you're really talking about an ensemble of theories. I don't know.
I think it is consistent, but the holographic dictionary is pretty clear about it, right? Once the state is out near the boundary, we know that it has to map by the usual dictionary to a mixed state. In the boundary theory, and the only way that I can think of getting such a state is by evolving the initial state with many different theories.
Or there's a coarse graining process involved. We forget about some of the micro.
Well, that is a specific version of coarse graining, but yeah.
Yeah, but I mean, it doesn't have to be that particular one. It could be that, there's some coarse graining involved where we forget about, we trace out some part of the Hilbert space and we get a larger entropy.
But if that standard seems too low, because we would have known how to answer that question many years ago. Like if I use standard n equals 4 super Young-Mills theory to evolve forward the state, I think I know how to coarse grain the out state. It looks more or less thermal, and I can just coarse grain over its microscopic properties, and I'll get a mixed state in that theory. So I think that we already knew the answer to.
I think maybe we're talking at cross purposes here. So when I say the Hawking calculation, I really mean the wrong calculation that gives you that begins with the wrong answer and gives you the wrong answer at the end.
Yeah, I mean that too.
It extracts the wrong state, and I think that wrong state is essentially the state that in fact goes into the outer entropy. I think that is the state, the maximizing state of the entropy. If I think that is the state that calculates the Hawking entropy for you. Mm-hmm. I'd like to prove it.
Yeah, that's a form of coarse graining.
Yeah, exactly.
All right.
Yeah. I think we're in agreement. I think we're just saying the same thing in different words and therefore disagreeing with each other because we're not using the same words to say it.
As always.
Any other questions for Netta?
Wait, sorry. When you say you want to reproduce the Hawking answer, are you talking about the outer entropy or the fine grain entropy for some state in the unitary theory that's supposed to like approximate the wrong state that Hawking would have used?
The outer entropy is a fine grained entropy for a state which is obtained by coarse graining information that we knew in the original state. So your either or is not actually an either or.
Okay, yeah, no, I see. Okay, thanks.
Final thing, not to Netta maybe, because Moshe, probably you answered that in QCD case, you use cluster decomposition to select the choice. Is it locality? So if you don't think about locality or anything, is it consistent not to include instanton if he's still around?
Is it consistent not to include?
Yeah, instanton. I don't know if somebody answered me still around.
I answered that before. Yeah, I'm just quoting Weinberg, the way he organizes the axiom of quantum field theory. So cluster decomposition is a specific, it's a specific version of locality.
Yes.
That's the thing that would break down if you quantize around one of the n vacua.
Yeah. Okay. So then still maybe a choice. Still maybe a choice because you're using locality as just a choice.
Well, it's a quantum field theory textbook, so you're stuck with
exactly.
anything that
I know. But
if you want to generalize that in various directions,
as a consistent at the level of quantum mechanics.
Yeah, but certainly I particularly don't know anything like that in quantum gravity. But yeah.
Okay. Yeah, I just wanted to understand if the choice issue is already involved in a non-gravitational level.
Yeah.
And thanks.
More questions? If not, let us thank Netta again.
Thank you.